Good morning, good afternoon, or good evening. This is question 9 of the Step 3 2024 paper. And with all of these videos, hopefully you've already had a go at the question yourself and you've either completed it successfully, well done, and you're looking for alternative thought processes to get through it, or you've had a go, you've got stuck, and you're looking for that little hint that will take you further through the question. As always, once you get a hint, do pause, see if you can use that to take yourself forward before you watch the entire spoil of the entire video. As mentioned in the intro to both this playlist and the Step 2 playlist, I often avoided the mechanics questions for the main reason you have to have a near perfect picture. You can't misinterpret anything, and even then it's very easy to make small slip-ups through the problem. So we're going to try our best with this question to have a really detailed, large picture with correct information, not making any incorrect assumptions about the scenario, and then being very careful as we proceed through. Let's have a read now of the situation. We have a large smooth table. X and Y axis line the plane of the table. A smooth sphere is placed with its lowest point at the origin. So if I'm looking side on, that means I've got my sphere and it's this point down here that I care about. A second smooth sphere has the same mass and radius, that's convenient, also lies on the table. Its lowest point is a y coordinate of, and my y coordinate's kind of deep in that way, and a large positive x coordinate. So this sphere is over here somewhere. Now if I try and draw this accurately in 3D, it's going to be really awkward. So I think I'm going to decide to draw this from bird's eye view. So I'm looking down at the table. So I have a y-axis and x-axis. Sphere A is centered at the origin. And if I'm looking down at this sphere, it does only look like a circle with its bottom point at the origin, i.e. the center of this circle as I'm looking down. It has a mass of m and a radius of r. And if in this same viewpoint I try and draw the sphere B, has the same mass and radius, its lowest point has y coordinate of, so this lowest point here is going to have y coordinate of 2r sine alpha, and the x coordinate is just some big positive value. That feels a little odd that they didn't tell us what it was, but we are then told it's projected parallel to the x-axis, so the motion is along here, so it's only the x-coordinate that's going to be changing. So that's convenient. That also has a mass of m and a radius of r. Now I'm a little worried, or one of the things I'm going to think about straight away before I continue reading, are these even going to collide? If I send this in that direction, we're only going to collide if the center here is close enough to the center of A, and basically we need this to be less than 2r, and radius of r for sphere B, radius of r for sphere A, and indeed, yeah, the y coordinate here is less than 2r, no matter what the alpha is, so we are always going to have a collision, irrespective of this alpha. Sphere B is now projected parallel to the x-axis with a speed of u, so that it strikes sphere A. So it's going to hit sphere A at some position here, and actually, because I can line the radii up like this, I believe, and I'm going to check this, that this angle here will be alpha. Because if I draw this right-angled triangle, then this side exactly is 2r sine alpha. Okay, so we know exactly how this collision is happening. I've kind of drawn the sphere B over here a little high up, but a bit of artistic license there. The coefficient of restitution is a third, so we'll probably be using that later on. So part I of the question is now wanting us to find the speed after the collision. Okay, so we have two equations for collisions. We've got a conservation of momentum and we've got Newton's experimental law. The awkward thing is that Newton's experimental law has to be applied perpendicular to the surface of collision. These are smooth. Yeah, smooth sphere. So there's no friction along this line. So along that line, everything is happy. And it's Newton's experimental law that happens in that direction. Which means we need to be a little bit careful when we come to choosing what our initial and final velocities are. I almost want to set up my axes not with the x and y axis, but in these two directions here, parallel and perpendicular to that contact surface. So then initially we have the speed of u meters per second, and then afterwards, and this is where my picture starts getting a little bit awkward, I'm going to say we've got I don't know where it's going, but some VB, which do I want to write in component form yet? Or do I just want to give it an angle relative to? Also, the awkward thing is the answer wants it in an x coordinate and a y coordinate. So I really should maintain that as much as possible. So I'm going to say that B is going to have a final velocity. I'm expecting it to be still in this kind of direction. It's going to probably bounce up slightly. And then A, I'm expecting to be in this kind of direction. So I'm going to call the B velocity. Yeah, I really don't like the mixture of the different angles that we've got going on. I'm going to call this one. I don't really want to use X and Y because they're normally used for coordinates. I'll say VB, WB for the X and Y coordinate. I'll call this VA and WA for the final velocities. And of course, the initial velocities for A are 0. So we don't need to worry about them. So let's set up our equations. And really what we want is the VB and WB, hoping that the VB is this top and the WB is this bottom thing. So let's do some conservation of momentum and Newton's experimental law. Maybe the easiest conservation of momentum is vertically. So vertically, using conservation of linear momentum, the initial momentum for both is 0. So the final momentum, WB times the M minus, I'm taking upwards to be positive here, so I should really just draw my arrow being upwards, minus WAM, which means that the WB is equal to the WA. Not surprising, if you're projected horizontally, then your two objects are going to bounce off in the same way vertically. Let's do the same for conservation of linear momentum. This time I'm going to take leftwards to be positive. So initially I have UM, and that is becoming VBM plus VAM, or U is VA plus VB. Okay, And then the last one, which is going to be our really awkward one, is our Newton's experimental law. So we know that the speed of, so we're doing Nell, we know the speed of approach is, well, this angle here is going to be an alpha, so that's going to be u cos alpha. So that's going to be my speed of approach. Now my speed of separation is going to be a lot more awkward. There's going to be a lot of combination, lots of combinations which correspond to that speed of separation. So really what I need is, so I have on B an arrow here for VB, an arrow here for WB, and I want the arrow there, which has an angle of alpha. So what's that going to be? So that's going to give us a VB sine alpha is pointing towards the collision, minus a VB cos alpha, because I can put another alpha here. Yep. And there, no, then it'll be a sine component again, won't it? Will it be a sine component? It looks like it should be a sine component because I'm wanting this component here. Sine alpha. If I were to think about it another way and put negative there, then that's my alpha. Yeah, it is the sine component. Okay, so that gives me my velocity along the line of centers for B. For A, we've got a very similar picture. The way I've drawn it, we've got VA going that way. We've got WB, nope, WA going that way. And really, need to be a little bit awkward because I've kind of implied certain things are positive and negative where they're kind of not, but I think it's fine. And I want the velocity into here, so that's negative of the velocity here. That angle there is alpha again, so this is going to be VA cos alpha plus WA. Now is this one definitely a sine alpha? Because that angle there's alpha again. Oh, why did I say this was sine alpha here? This should be a cos alpha. So one of the alarm bells that was going on in my head as I was doing this is almost always these two components, these two trig terms, are opposite to one another, which indeed should have been the case if I didn't make that error there. So therefore the speed of separation, well actually this we wanted the opposite signs because we're pointing the wrong way. So now my speed of separation, as I've written it this way round, I've got both arrows pointing into the point of collision, because really this is this arrow here. To find their speed of separation, I'm going to add these two arrows together. So that's going to be VB minus VA, lots of cos alpha, minus WA plus WB sine alpha. So now if I use Newton's experimental law, which says E equals separation over approach, that tells me that this speed of separation is equal to a third of the speed of approach, u cos alpha. Okay, now I would quite like to get rid of the WB, sorry, the WA and the VA. And I'm still missing an equation, which is going to be, it's going to be the other components, isn't it? So I am going to need the, so these were velocity along centers. I am going to need the velocities parallel to the surface of collision or perpendicular to the line across the centers. So if I do get rid of my VA and my VA and WA here, so the VA is U minus, so this is going to be 2VB minus U cos minus 2 lots of WB sine equals a third U cos alpha. And I'm also going to try and make the other velocities, and they're going to have to be no, I just need so parallel along this line here, the velocity of B cannot change, because along this line there has been no collision whatsoever. So parallel to collision surface, the velocity of B is unchanged, and that also means that the velocity of A along that line should be 0. So what was the velocity of A initially? It was U sine alpha is going to have to be equal to the velocity afterwards. So U sine alpha is in that direction, so I want the velocity in that direction, so that's going to be VB sine alpha plus WB cos alpha, and a good little sanity check, it is just swapping the sine and cos terms over. You had to be careful with the sines though. Okay, so now we have our two simultaneous equations for VB and WB, both of which are really quite awkward. If I'm looking at what the answer looks like, WB looks like it might be the simplest to create, but doesn't look like it's the simplest to create from these. So I'm going to call this equation 1 and equation 2. And if I do equation 1 times cos plus 2 sine alpha lots of equation 2, that's going to cancel my WB terms, because both of them will have a 2 sine cos with opposite signs. So that's going to be 2VB minus U cos squared plus VB sine squared equals a half U cos squared plus U sine squared. Now, does this lead to the expression that I have there for VB? I'm going to have to do some manipulations. On this side, I can factor out the VB stuff, which is as 2 cos squared plus a sine squared lots of VB. The minus U cos squared I'm going to throw to the other side. So that's going to be 4/3. I'm not liking that it's 4/3 because I'm not expecting any 4/3 in the final answer. Now the question, well, I'm going to have to divide by this thing, which is, oh, I've forgotten the 2. Have I forgotten the 2? I've forgotten the 2. I'm timesing it by 2 sine alpha. So 1 plus 2 lots, so there's a 2 here, and then plus 2 lots of the u sine, so there's a 2 here. So there's a 2 there, and I can factor that entire 2 out, and that's a 1. So that's really pleasing. This bracket here is just cos squared plus sine squared is 1. So therefore VB, if I divide everything by 2, is u 2/3 cos squared plus sine squared. And I want this to write this purely as sine squared, no cos squareds. So this is u 2/3 1 minus sine squared plus sine squared. I'm expecting a negative 1/3 to come out, but I'm not, because my VB I've got pointing to the left, so I'm going to have the exact opposite sign here. So this is going to be 1/3 lots of, except I've got my, this is a third u, I've got is 2 plus sine squared, rather than 1 plus 2 sine squared. So where have I got a 2 being put on the wrong section of this? Adding that does give me the 4/3, which I was getting. And it is, I am working out VB, which in my picture is the x coordinate of the velocity afterwards. Where has my 2 gone? Double check some of my other substitutions. This thing up here, I use the fact that VA equals VB minus U. Okay, here we go. VA going in here. Oh, isn't that more worrying? VA, no, because I've rearranged this the wrong way around. So I did do it right the first time. U minus VB. So putting that in, I am getting a minus U and I'm getting a minus VB. WA is equal to WB. And of course, in all my pictures, I'm taking these to be the modulus. So I shouldn't have really written them in vector form, rather than what I'm thinking of them as 2 separate arrows. And then when I do put them in vector form, I need to remember the minus signs. I did equation 1 times cos, and equation 2 times 2 sine. So that does indeed destroy the WB terms. So why have I got the wrong thing in the wrong place? Because everything else is correct. Actually, hang on. No, that's fine. I was a little worried about my expanding of this and simplifying of this with the third pulled out. But I am getting a minus 2 sine plus 3 sine because of the third that I factored out. Really, I want this to still be a third. If that thing there was still 1/3, I'll be happy. So where did that come from? That came from this term here. So I really want this to be 2/3. So really I'd like this term to be negative. So why is this term here negative? Because u cos alpha or I want the entire this side to be the opposite sign. So I've got a sign error is actually the issue. My speed of approach is u cos alpha pointing towards the intersection. My speed of separation, I think that's simply it. We have this thing should be the opposite way round, because that speed of separation really looks negative. So really I want to swap the sign of that, which is equivalent just to swapping the sign on the other side. So the speed of separation really is the modulus of whatever that subtraction ends up being, and that subtraction really looks negative. So it does feel a bit fudgy at the moment, but that's because it's an applied question. I'm gonna just go with it and let it happen. So I'm going to put the negative sign in there, the negative sign in there, which means I put the negative sign in there, which means this thing is 2/3. So when I halve it, it's 1/3. So that's 1/3. And this thing was 1 plus 2 sine squared. Really, I should justify that a little bit better. And one of the big things here is I'm writing my solution straight away with a question which you're a bit shaky with. I do recommend having some scrap paper to work through this algebra first. And then when you write it in, it doesn't quite look like you fudged it quite as much. Because I should have just written that subtraction there the opposite way round. Okay, so that was the VB. Now I want to find the WB. So I want to do a similar thing. I could substitute this VB back in to one of my original equations. That second one looks nicer. Or I could try and resolve. Resolving by doing a different combination of equation 1 and 2 might work. Because I didn't manipulate this very well, which I probably should have rearranged equation 1 to put all the u's on the same side. Because I didn't do that, that feels more difficult. So I'm going to go sub into equation 2. So equation 2 says now that u sine alpha equals 1/3 u 1 plus 2 sine squared alpha. What does it say? I've lost the equation. There it is. With an extra sine alpha on, plus WB cos alpha. So somehow I want to divide through by cos alpha upon doing some rearranging. So where am I going to get a common factor of cos alpha from? If I do look at the answer, we've got a single sine, a single cos. So everything does need to collapse in some way. So let's start rearranging it. WB cos alpha is equal to, I'm going to have 1/3 u. I'll factor out the sine alpha as well. So this side is just a 3 inside the bracket, minus 1 plus 2 sine squared. Oh, and this is going to actually be really pleasant. So this is 1/3 u sine alpha. The bracket is now 2 minus 2 sine squared. So this is 2/3 u sine cos squared. So WB equals 2/3 u sine, and one of the coses is cancelled. So that squared is gone. So thus, the velocity of B is, and remember we had to swap the sign of this VB because it's opposite. It's pointing to the left. My arrow VB was pointing to the left. U sine alpha cos alpha, and I will reference that this was as VB's arrow pointed left. So when you put it in as a vector, it comes out as negative. Okay, that was a lot of hard work already just for part I. Probably more efficient ways to do it, but this is why I avoid mechanics questions. I could have done that a lot cleaner, for certain. Part 2 then. Let's hope the rest of the question now follows quite nicely. Show further that the lowest point of sphere B crosses the y-axis at the point y, 0, where that and tan beta is that stuff. So we now have the velocity of sphere B, so we know what direction we know that the direction of sphere B. So you can write down the position vector of that bottom point. The position of base of B will be, I'm basically using, what am I using? S equals, no I'm not. I'm doing a R equals R naught plus UT style. Yeah, really, if you look at the Suvat equation, this has a plus half AT squared on it, but the acceleration after the collision is 0. So that's going to give me my velocity, my position of B at a general time afterwards. So we know the position, or we can work out the position where the collision happened, which is this point here. So that was 2r sine alpha was the y coordinate, and the x coordinate will be 2r cos alpha. So the position is 2r cos alpha, 2r sine alpha, plus t lots of the velocity of B, which is negative a third u, 1 plus 2 sine squared alpha, 2/3 u sine cos. So that's now going to be the position of B at any time t, at time t after the collision. Okay, so now we're going to cross the y-axis. So then cross y-axis implies that the x coordinate of the position vector is going to be equal to 0, i.e. 2r cos alpha equals a third ut 1 plus 2 sine squared alpha. So then t is equal to 6r cos alpha over u 1 plus 2 sine squared alpha. I've times that by the 3, I've divided by the u and the bracket. Now I'm having a quick look that this thing looks a little bit like the tan beta. Do I want to write this in terms of tan beta straight away? Or do I want to put in the... I'm going to write this in terms of the tan beta. So the tan beta was 2 sine alpha. So I'm going to have 3r over u tan beta but tan beta had a sine alpha in that I didn't want. So I can write it as so, with tan beta as given. And if I do just double check, if I put everything in the places the sine cancels, the denominator works, the numerator works. Okay, so nice. So then we cross y-axis at ry. I shouldn't be underlining these because these are just coordinates rather than an entire vector. So the x coordinate and the y coordinate, so ry is going to be 2r sine alpha plus t, which is 3r tan alpha over u sine alpha times 2/3 u sine alpha cos alpha. That's absolute chaos. But let's see what happens. The u's cancel, the 3's cancel, the sines cancel, and I'm going to be left with 2r. That term leaves me with a sine alpha. The 2 and the r on the other one can come out, leaving behind a tan beta and a cos alpha. Is that what the question asked for? It was, so as required. So we've worked out then where sphere B eventually crosses the y-axis. A third sphere. So we've now got a third sphere, which is at rest with its lowest point at h, 0, where h is some positive value. So we have a third sphere now sitting somewhere up here at h. And we want to show that if... the question named that thing capital Y. So I'll also name it capital Y. So we want to show that if h is bigger than that, sphere B will not strike sphere C in the collision in its motion after the collision. So we now have, and I'm going to draw another picture to go with this. So we need these two to miss each other. Basically, we have sphere C positioned at H, and we're going to have sphere B centered at Y when it goes across the y-axis. So we certainly need y, so we need y plus 2r, to be less than h, which isn't quite what their condition is, because we could have collided afterwards. Remember, B is going in this direction, so it might have collided a little bit later on rather than directly at that time. Now, the worrying thing is it's using this angle beta. Now, we made up the angle beta. We didn't really interpret it particularly well. We just said, hey, look, let tan beta be this thing. If we try and interpret it, well, it looks like tan beta is the ratio of these two. So it's actually, yeah, tan beta is actually the angle with the x-axis, because this is kind of a... No, it's the angle with the vertical, because... Yeah, so let's try and interpret this tan beta a little bit. We have B, and this probably was a better way to do the previous part of the question. B's going in this kind of direction, with that component being negative 1/3 u 1 plus 2 sine squared, and this component being 2/3 u sine cos. I didn't need that bracket there. So if I were to call this angle here, no, I want which is a bit weird. I want this angle here. If I call that angle there beta, no, I was right the first time. If I call this angle here beta, then tan beta is the opposite, which is the same vertical component of velocity over the adjacent, which is the x component. The sign can disappear because I'm talking about lengths of vectors again rather than directions. So really this means that beta is the angle of B's final velocity. So now I've interpreted a little bit more what this beta is. I can go back to my picture here. So then this is B's velocity at an angle of beta. And we basically need, well, let's try and find the shortest distance between the center. So actually I'm going to be moving B slightly further along its path so that this here is a right angle, because then that's the shortest distance between the two radii. So that length there, I should call this, should probably give some things some names. I call this the center of C. That can be called, I probably need better names than this. Let's call this D, E, and F. So then EF is the shortest distance So now I'm kind of using ideas within the world of vectors, shortest distance between a point and a line in vector world. EF is the shortest distance between centers, which means that EF has to be greater than 2r to avoid collision. But we can work out what EF is, because we have the triangle here. You've got this side being h minus y. You've got a right angle there. And this angle here is beta. So this angle here is beta. But EF is h minus y cos beta, and that's where my sec is going to come in. So that means that h minus y cos beta has to be greater than 2r. H minus y is greater than 2r sec. So h has to be greater than y plus 2r sec. And if we do go back to our kind of first thought, this still does hold. Sec is always strictly bigger than 1, certainly for acute angles. So that condition automatically holds with this slightly stronger condition being put on. Okay, part 3 done. Part 4. Okay, there is a cut in the video here. I did spend maybe 15 or so minutes tackling part 4 with no real success. I'll show you the what I came up with. If you do want to pause and try and think, what was I trying to go on about? I was trying to do it in a very geometric way. Now I have gone and picked out a hint, and I'm going to re-tackle now part 4 using that hint that I've spotted. And unfortunately, it wasn't a geometric argument as you might be able to work out from these pictures. I was trying to work out, put some inequalities on some lengths of lines, but actually part 4's first inequality is to do with the condition or the equality that we had for y already. So previously we've shown that y is 2r cos alpha tan beta plus sine alpha, and we can factor out a sec beta. We factor out a 1 over cos, so this is going to be left with cos sine plus sine, and factoring out 1 over cos out of something basically puts a cos there, and you can check that by expanding the brackets out. So this thing is equal to the 2r sec beta that I cared about, and using our addition rules for trig, we get a sine alpha plus beta. So this, and we know sine alpha plus beta is always less than or equal to 1. So this is strictly less than 2r sec beta, provided that sine alpha plus beta is not 1, i.e. alpha plus beta is not pi by 2. So we need to justify, because otherwise this is just a less than or equal to. We need to justify why this alpha angle and this beta angle cannot add to pi by 2. And there are probably multiple ways of doing this. The way I've thought is by looking back at our picture and actually finding where these angles are. So this is the line between the centers, and this angle is alpha, and then the velocity, the final velocity of the object B is at an angle of beta. That's what we justified up here by reinterpreting what the angle was. So why can these two angles not add up to pi by 2? Well, if they did, I can bring this angle back down here and say the angle there is beta, which will mean, so if alpha plus beta equals pi by 2, then this angle here has to be a right angle. The direction post collision of B is perpendicular to the collision surface. So that's sorry, let me get that back. The collision surface, which is this dotted line here. So if that was at a right angle, no, it's not perpendicular to, it will be parallel to the collision surface. But if you're parallel to the collision surface, then your perpendicular, well, your momentum in this direction had to be equal, but A had no momentum in that direction. So B has to have some momentum in the non-perpendicular, the non-parallel to the surface direction, which is a contradicting conservation of momentum along the line of centers. If we did travel in that direction, the momentum in this direction would not be conserved, so it can't be. So alpha plus beta cannot be pi by 2, so we do indeed get the fact that y is strictly less than 2 sec beta. So now we want to show, hence show that the sphere B will not strike C again for any value of alpha if h is bigger than that particular value. So we would like to maximize this part here. So in the previous part, we showed that h is always bigger than this thing. So if we can find the maximum of this expression, then we can say that if h is bigger than that maximum, then it's certainly going to be bigger in every single possible situation. So let's let f of, and beta is all dependent on alpha, so f of alpha be this y plus 2 sec beta. And we want to find the maximum. Well, we can say that this is always smaller than 4r sec beta, because y is less than the 2r sec beta. So I'm trying to maximize this, where sec beta is a very particular thing. So I'm actually going to, do I fancy doing that? Yeah, I'm going to actually consider f squared of alpha, so I can find the maximum value of f squared, and then I'll square root the answer, which kind of looks like has happened with that over root 3 going on. So f squared of alpha, again, is less than 16r squared sec squared beta. And the reason I've done that is sec squared is tan squared plus 1. Tan squared beta plus 1. And I know what tan squared beta is, or I know what tan beta is by part 2 of the question. So this is going to be 4 sine squared cos squared over 1 plus 2 sine squared squared plus 1. And I'm going to call this, because it's not really f that I'm differentiating anymore, I'm going to call this g. So I want to find the maximum of this g function now. To find the maximum, we need to differentiate it. Now r is fixed. So actually, I'm going to be a little bit sneaky here and actually call this 16r squared g alpha. So g alpha is just the bracket. To differentiate this, I'm half considering simplifying the numerator using the double angle form to turn the numerator into sine squared of 2 alpha. That's surely going to be easier, because then I don't need to do extra product rules. G of alpha is going to be sine squared 2 alpha over 1 plus 1. We did have an expression for y. Actually, I'm now half considering maybe I should have used the expression of y here rather than the bound for y. Because each time we put a bound, we're making things weaker. It depends how strong that bound is. And I think it's fine to use the bound because we're doing it over all alphas. So actually, for some alphas, this inequality is going to be very almost an equality. So we might as well use it to simplify our work. Okay, I still need to differentiate this g of alpha, which still is not simple, but it's going to be the derivative of the numerator times the denominator minus the derivative of the denominator. It's going to be 4. Differentiating that denominator, it's actually going to give me 8 sine alpha cos alpha times the numerator, and I still have a copy of that bracket on there, over the denominator squared, and then that plus 1 just differentiates away. Just going to very quickly mentally check that I haven't done anything silly there. First term looked good. Differentiating the second term, I'm popping out an 8 sine alpha cos alpha, yeah. So then g dashed of alpha equals 0 when? So some things can cancel out straight away. So on that first term, there is a sine 2 alpha in both sides that can disappear, and a copy of the bracket that can disappear, equals 8. I've still got the sine alpha cos alpha, a single copy of the sine 2 alpha. So when does this equation hold? I would have quite liked more things to have cancelled out. Certainly there's a 2 that can cancel. I can write this as sine squared 2 alpha. I could rewrite everything in terms of 2 alpha almost. We do have a relationship for sine squared turn into cos 2 alpha. It's not quite the right identity. Cos 2 alpha is 1 minus 2 sine squared. So the 2 sine squared can be written as 1 minus cos 2 alpha. So do I want to do that is the thing. Well, I can cancel the 2's out. So this is going to be cos 2 alpha. That's going to be 2 minus cos 2 alpha equals, and on this side 2 is cancelled. One of the 2's I'm going to use in with the sine 2 alpha, and this looks horrendous. Oh, this is now sine squared 2 alpha. So I can make this completely into a quadratic in cos 2 alpha. So 2 cos minus cos squared 2 alpha equals 2 minus 2 cos squared 2 alpha. I'm really hoping this comes out as a pleasant solution, because if it's not pleasant, it's going to make a lot of things, as I put these back in, incredibly unpleasant. So I'm adding that. Plus 2 cos 2 alpha minus 2 equals 0. Now that quadratic does not have a nice solution. So was it smarter to have left things in terms of alpha? We've definitely made our life more complicated than it needs to be. So is there any other smarter things I could have done? I'm trying to maximize here. I'm basically trying to maximize sec squared, which is basically trying to maximize tan squared. The plus 1 changes the maximum value, but it doesn't change when that maximum value occurs. Trying to maximize tan squared by differentiating it is incredibly unpleasant, and I've arguably made it a lot more unpleasant by making it 2 alphas. So is there something I could have done better, or is it worth fighting this a little bit longer? Because this doesn't have a nice solution at all. I think there's some things we could have done to make this a lot less. So we seek to maximize this sec beta, which is equivalent, because sec squared equals tan squared plus 1, this is equivalent to maximizing just tan beta. If we want the biggest, and again we're in acute angles only, so everything's positive, the biggest sec beta is going to be at the same time, at the same angle beta as the biggest tan beta. So I'm now going to say let f of alpha just be the tan beta. So I'm not even going to bother squaring it. And I think that will make the calculation of the derivative a lot simpler. So now f dashed of alpha, and again, I don't think I want to go into double angles here. That seemed to have made my life a little bit more difficult than it should have been. So then if I differentiate that top one, it will be the derivative of 2 sine alpha, which is 2 cos squared, minus 2 sine squared times by the denominator. So that was derivative of the numerator, had to have a little bit of a product rule in there, times by, or subtract the numerator times the derivative of the denominator, which is going to be 4 sine cos over the denominator squared. So this thing, so then f dashed of alpha equals 0 when the numerator equals 0, which is not pleasant at all. How can I simplify the numerator without giving another headache? Not particularly easily. So let's just do it. So this is going to be 2 cos squared alpha minus 2 sine squared alpha plus 4 sine squared cos squared minus 4 sine to the 4, eek, that's not very pleasant, minus 8 sine squared cos squared. And this thing is equal to 0. Things to cancel or to think about. We can get rid of, we can turn all the sines into coses or coses into sines. There's a few terms that can simplify. So I'm going to turn everything into sines. 2 minus 2 sines squared. Reason I've chosen sines is because this term I really don't want to touch. Minus 4 sine 4. Then I've got minus 4 as those two come together. Sine squared 1 minus sine squared. Still equal to 0. And the 4 sine to the 4's cancel. Lovely. So I'm going to be left with 2 minus 8 sine squared alpha equals 0, which means that sine squared equals a quarter, and because we're in acute angles only, as alpha is acute, we have that sine alpha equals a half, which also gives that cos alpha is root 3 over 2. Knowing that little pairing is quite helpful, which then means that tan, so now tan beta, which was what we were trying to focus on, which is the f of alpha, is 2 lots of a half, lots of root 3 over 2 over 1 plus 2 lots of a quarter. So what does that leave behind? The numerator is going to be root 3 over 2. The denominator is 1 plus a half. It's just 3 over 2. So tan beta is root 3 over 3. So then finally, this y plus 2r sec beta is less than 4r sec beta, which has to be less than when this thing is maximal, which is 4r. Oh, I actually need to still find sec beta, don't I? Because we've got tan, so sec squared beta is 1 plus tan squared. Tan squared is a third, so that's 4/3. So sec beta is 2 over root 3. This is times 2 over root 3, which equals 8r over root 3. And as h is less than this, if h is less than, or sorry, is now bigger. Was h bigger? H was bigger. As h is bigger than this, if h is bigger than 8 root 3, 8r over root 3, then the condition holds for any alpha, i.e. the spheres B and C do not collide. Ooh, quite a large final part of that question. And the hint which I looked at did go through this differentiation calculation to kind of fix this maximum point. But if you find a more efficient way, one based like I tried to do in a more geometric way, I'll be very interested. And if this 8r over root 3 has some proper interpretation in the problem, rather than just coming out from this calculus style approach. Anyway, sorry for the cut in the middle of the video, and it didn't all come together in one go, but the rest of the playlist will have more of these questions for you to peruse.